Hello friends, morning. In the breakdown mechanism of solid dielectrics, so far I have explained intrinsic or electronic breakdown, electromechanical breakdown, electrochemical breakdown, and electrothermal or thermal breakdown. Today I will discuss remaining breakdown mechanisms. They are cracking breakdown, ring breakdown, and breakdown due to partial discharges or breakdown due to cavity. So in the sequence, fifth number is breakdown due to cracking. This is the experimental setup for explaining the cracking breakdown. Cylindrical electrode, upper one connected to high voltage, circular electrode, lower one connected to ground or earth, and in between these two electrodes, there is insulation paper. Now I will recall three definitions. One is breakdown or puncture voltage. Breakdown or puncture means when current flows through the insulation. Second is spark over or flashover when current flows over the surface of the insulation. That is spark over or flashover. And third is creepage distance. Creepage distance is the different distance between high voltage point and earth point over the surface of the insulation. So from this point up to this point, if we measure the distance over the surface of the insulation, that is called as creepage distance. Now I will explain how the tracking occurs. When this insulation paper is exposed to the atmosphere, then a layer of moisture gets deposited on the surface of the insulation paper. Let us say this is the moisture layer. Now current starts flowing through this moisture layer from high voltage electrode to the ground electrode. When continuously current flows, at some points, the moisture may get evaporated. Let us say at this point, moisture gets evaporated. Then there is break. And then current starts jumping through this. But it is flowing through the over the surface of the insulation paper. So at this point, the insulation paper gets eroded. Now this phenomena is repeated and there will be eroded points on the surface of the insulation, and finally we may find complete surface gets eroded and large current flows and insulation breaks down. This type of phenomena occurs after prolonged operation, but it can occur at low voltage also. The voltage required to cause or to form the track on the surface of the insulation paper is called as tracking index. In another case, if we apply high voltage in the beginning, even when there is no moisture level, we apply the high voltage, and if this voltage is not sufficient to cause the puncture or breakdown, but it is more than the spark over voltage, then a spark over occurs over the surface of this insulation paper. This type of discharge is called as surface discharge or also called as sliding discharge. It occurs over the surface of the insulation paper. When this type of discharge occurs, we can observe a track on the surface of this insulation paper. On this track, the dielectric strength of the insulation paper reduces. And if this phenomena is repeated, then finally a breakdown occurs at the point on the track where the insulation paper is weak. So this is about tracking breakdown. I will show the track formation on the surface of this type insulation paper, on the surface of this type insulator. See, this is the disc type insulator. This is also disc type insulator. Here you can observe this track. So this is the track formed on the surface of this type insulator. And on this track, the dielectric strength of the insulation has reduced. You can have the better idea about this tracking phenomena and gliding discharge through this experiment. Experiment is tracking phenomena and gliding discharge on the surface of PVC insulation paper. I have uploaded a video showing this experiment. This is the link for the video. You can get the better idea about tracking phenomena and gliding discharge on the surface of PVC insulation paper through this experiment. Next phenomena is breakdown due to treeing. Treeing. So this type of breakdown is normally observed in cable because thickness of the insulation is required here. So let us say this is the cable insulation. In the cable insulation, one side is connected to the core, so that is connected to high voltage, other is connected to the earth. So let us say this side is connected to high voltage, this is connected to earth. This is the insulation paper or insulation in general. This is a cavity inside this insulation. Cavity is also called as void. This cavity is either filled with moisture or some gas or air. Obviously, the breakdown voltage of this cavity will be less than the breakdown voltage of this insulation because this cavity is filled either with gas or air or moisture. So this is the first requirement for causing the tree. Cavity should be there. Cavity or void should be there. Now when we apply voltage for long time, then breakdown of this cavity takes place. Now this breakdown does not occur in between this cavity and the ground immediately, but this breakdown occurs nearby on in the surface near to this cavity. So a tree-like structure is observed from this cavity up to the point. Now this tree-like structure with time starts progressing towards the earth. So here I have shown in this third diagram, this tree-like structure has approached the ground and through this the breakdown occurs. This type of breakdown also requires long time. It is not immediate breakdown. If voltage is very high, then there is immediate breakdown. But at normal working voltage, this breakdown is not immediately, does not occur immediately, but it occurs after some prolonged time. So this breakdown occurs through the tree-like structure. Therefore, the name is tree breakdown. I will show the diagram for this tree breakdown. This is the high voltage electrode. From here is the cavity, and through this cavity, the breakdown has started, and it is approaching the other end through this tree-like structure. As it is forming tree-like structure, it is called as tree breakdown. But it is through the insulation paper. And if this type of breakdown occurs over the surface of the insulation paper, then it is called as tracking breakdown. So difference you should remember: over the surface it is tracking, through the surface it is treeing. So this is electric tree that is occurring through the insulation paper, and this is tracking because it is occurring over the surface of insulation paper. So this is the difference between tracking and treeing. Common factor is both the breakdown do not occur immediately, but they occur after prolonged operation if the insulation is under working voltage. It is not subjected to high voltage. The last one is breakdown due to partial discharges, PD. PD is partial discharge. So first I will explain the mathematical model and corresponding equation. Then I will explain the mechanism. Let us say this is the insulation. It is healthy insulation. There is no cavity or void. So its electrical equivalent is capacitance. I am assuming ideal insulation. Therefore, I am not showing the resistance in parallel with this. I already explained the electrical equivalent circuit of ideal insulation, practical insulation, and unhealthy insulation. So, ideal insulation, capacitance, practical insulation, capacitance and resistance in parallel or in series. And when we show the cavity or void in the insulation, then it is not healthy insulation because it has some cavity or void. This cavity or void is filled with either moisture or air or gas. So this is the insulation with void or cavity. So electrical equivalent circuit is like this. This insulation we can divide into three parts. First one, so capacitance will be C. This part capacitance is also C. So these two C I am combining and representing as single branch C. Then this is the third part. So this capacitance says C2. This is also C2. We are combining these two and representing like this C2, and C1 is the capacitance of this cavity represented by C1. Capacitance of cavity or void is represented by C1. So this is healthy part. This is the part with void or cavity. So when we are applying the voltage, here the voltage distribution will take place. Say this is voltage V1 that is across the cavity, and V2 is the insulation, voltage across the healthy part. Expression for this V1 is this one. V applied voltage into D1. D1 is the diameter of this cavity because for analysis purpose, we assume that cavity is spherical in nature. So D1 is the diameter of the cavity divided by D1 plus epsilon 1. Epsilon 1 is the relative permittivity of the cavity into D2. D2 will be equal to, if this insulation has thickness D, this is D1, then remaining portion will be D2. D2 is D minus D1 divided by epsilon 2. Epsilon 2 is the relative permittivity of this insulation. So this is the expression for the voltage appearing across this cavity. Now I will explain the mechanism. Now I will explain the phenomena. V1, I already given you the expression for the voltage appearing across the cavity. This is the cavity. Voltage appearing is V1. This is the electrical equivalent circuit. C, C2, C, C2 and C1. C1 is the capacitance of the cavity. Now when these are the corresponding waveforms, V is the voltage applied across the insulation. V1 computed according to this equation is the voltage appearing across the cavity. Vi is the inception voltage. Inception voltage means the voltage required to cause the breakdown of the cavity. Let us say this cavity has diameter of 1 mm and it is filled with air. Now, dielectric strength of the air is 30 kV per centimeter. So for 1 mm we require 3 kV for causing the breakdown. This 3 kV will be the peak value. So if this cavity is filled with air, has diameter of 1 mm, then this inception voltage will be 3 kV on positive side as well as on negative side. So if this V1, that is voltage appearing across this cavity, is more than 3 kV, then obviously there will be breakdown of the cavity. So when we apply the voltage V, V1 is appearing, V1 is increasing, and at this point the breakdown of the cavity will occur. Breakdown of the cavity will occur means this is as good as closing of this switch. This path will be short circuited. So current will flow. When current flows, heat is generated in this cavity. So due to this heat and the voltage, there will be breakdown of some material around this. At this point, the voltage will collapse because cavity has broken down. So again, the cavity will regain the dielectric strength. So when it is regaining the dielectric strength, voltage is increasing. So as soon as it becomes more than Vi, again there will be breakdown of the cavity. So at this point, when breakdown of the cavity occurs, we observe the current pulse. So this process is repetitive. So we observe the pulse on positive side, corona pulses, or this current pulses on positive side as well as on the negative side. When this process is repetitive, the breakdown is continuous there. Continuously breakdown is there. So from this point, tree-like structure is established up to the earth point, and finally there will be breakdown. So in this case also, due to these repeated partial discharges, the breakdown occurs and breakdown channel is established in tree-like fashion. So breakdown due to treeing and breakdown due to partial discharges, we can say they are similar. The reason is partial discharge. Now here this is called as partial discharge because it is taking place in simple cavity, just in cavity. It is not occurring between the entire thickness of the insulation. Therefore, it is not called as discharge. It is called as partial discharge. So due to partial discharge also, the breakdown occurs after prolonged operation. However, it depends on how much voltage is appearing across the cavity. If this voltage which is appearing across the cavity is less than this inception voltage, then there is possibility that there is no breakdown of the cavity. Obviously, there will be no breakdown of the cavity, but with prolonged operation, the diameter of the cavity may increase. And when diameter increases, the voltage required to break down, voltage appearing across the cavity, that will also increase. And it may cross the inception voltage of the cavity, and there will be breakdown. So this type of operation also occurs after prolonged time. Now I will take one numerical to explain how this voltage is obtained and how safe working voltage is computed. Now let us see the numerical on this. Numerical is solid dielectric specimen of dielectric constant 4 has an internal void of 1 mm thickness. Thickness of specimen is 1 centimeter. It is subjected to voltage of 80 kV. The void is filled with air. First part is find whether internal discharges occur in the specimen. Second part is if yes, find the voltage at which the internal discharges start. Third part is draw the necessary voltage and current waveform. So just now I had explained this partial discharge phenomena. V1 is the voltage appearing across the cavity. So let us solve the first part. It is given by expression V d1 upon d1 plus epsilon 1 upon epsilon 2 into d2. V1 is voltage across the cavity or void. Here the applied voltage is 80 kV. Now nothing is mentioned about this voltage. We assume that it is RMS value. So V is 80 kV. Epsilon 2 is the permittivity of the insulation. It is given 4. D1 is the thickness or diameter of the void. It is given 1 mm. D is 1 centimeter, that is total thickness of the insulation is 10 mm. So D2, that is thickness of the healthy part, is 9 mm. So V1 we are getting 24.6 kV. Now epsilon 1, here epsilon 1 is the relative permittivity of the medium. It is filled with air, so it was 1. So by proper substitution we are getting V1 is 24.6 kV. Now as cavity is filled with air and thickness is 1 mm, its breakdown voltage will be 3 kV because 30 kV per centimeter is the dielectric strength of the air, where 30 kV is the peak value. So obviously 3 kV will be the breakdown voltage for 1 mm thickness, and this 3 kV will be peak value. So RMS value will be 3 divided by root 2, that is 2.12 kV, that is RMS value. Now this is the voltage required for breaking the cavity, 2.12, and voltage appearing across the cavity is 24.6 kV. So obviously the breakdown of the cavity will occur. Now the second part is if yes, find the breakdown, find the voltage at which the internal discharges start. So on the waveform we have to find the voltage at which the internal discharges occur. Alternatively, we can ask this part as find the safe working voltage for this insulation. Safe working voltage means the internal discharges should not occur. So in order to avoid the internal discharges, the voltage appearing across the cavity should be less than or equal to 2.12 kV. So V1 is 2.12 kV. So corresponding voltage we have to obtain. So this is the equation. So corresponding voltage we obtain is 6.89 kV. That is RMS value. So if voltage applied to the insulation paper is 6.89 kV, then voltage appearing across the cavity will be 2.12 kV RMS value. And as this is not sufficient to cause the breakdown of the cavity, the internal discharges will not occur. Now, third part is I will show the corresponding waveforms. So these are the waveforms. Nomenclature are slightly different. So this is the applied voltage, which is 80 kV RMS. This is the voltage appearing across the cavity that we obtained around 24 kV. V is the inception voltage. For this cavity, we obtained this as 2.12 kV RMS. On the negative side, this will also be 2.12 kV. So as soon as the voltage across cavity reaches 2.12 kV, the cavity breaks down. So there will be collapse of the voltage. So at this moment, the current pulse we observe. This is the corona or partial discharge extinction voltage. So from here also the current or voltage will start increasing. It is increasing according to this VC. So again at this point it is crossing 2.12 kV. So there will be breakdown of the cavity. So this voltage will collapse. Here current pulse we obtain. At this point the extinction will appear. There will be extinction of the breakdown voltage or cavity will regain the dielectric strength. So here again the voltage will start increasing, but as this is going on the negative side, this will also go on the negative side. So on this side, this is the corona inception voltage. Sorry, this is the corona inception voltage. So at this time also the breakdown will occur, voltage will collapse, and here we observe the current pulse. So this is how the voltage and current voltage is appearing across the cavity and current pulses are observed across the cavity. So that is all about the breakdown mechanism in solid dielectrics. So that is the end of first unit. In this first unit, I have explained the breakdown mechanisms in gaseous, liquid, solid, and vacuum dielectrics. I have explained the different types different types of electric fields, how they affect the breakdown voltage, how they affect the breakdown. I have explained Townsend's breakdown mechanism. I also explained the factors which affect the breakdown mechanism in gaseous, liquid, and solid dielectrics. So I hope this these videos will be useful for your academics. Thank you.